YouTube channel some point this afternoon. So if you've missed any of our previous meetings, you can also go back and rewatch those. So it's my pleasure today to welcome back a couple of CfA alumni who need little introduction. Our first speaker today is Dr. Hannah Diamond-Lowe, who is joining us from the National Space Institute at the Technical University of Denmark. And Hannah completed her bachelor's at the University of Chicago before, of course, moving to the CfA, where she completed her PhD in May of last year. And Hannah's work focuses on characterizing small exoplanet systems, both via transmission spectroscopy of their atmospheres and by analyzing the high energy spectra of their host stars. And today, Hannah is going to be talking about her work in combining both these areas in the analysis of the LHS 3844 system. And the title of her talk is the LHS 3844 system, transmission spectroscopy of the rocky exoplanet LHS 3844b and the high energy spectrum of its host star. So Hannah, if you go ahead and share your screen, please.
Sure. Thank you so much for that introduction and that you bravely read out the whole title. So I won't do it again, but yes, I'll just reiterate that we're talking about the whole LHS 384 system today. And I, of course, would like to thank all of my collaborators who've worked with me on these projects. So because I'll be switching from kind of talking about the star to the planet, I tried to make a sort of handy little key here in the corner to let you know when we're talking about the star or the planet or both. So we'll start off with both to give you kind of a picture in your head of what this system looks like. So the star LHS 3844 is a nearby mid-M dwarf, and we consider it fairly inactive. It has a long rotation period, no visible H-alpha in emission, all the indicators you'd look for. And then there is a planet around LHS 3844 that was discovered in the TESS data initially. And this planet is terrestrial in nature, and it is also super hot. It has a very short orbital period, and it's very highly irradiated. So I'm just kind of putting it in context as well of the small planet radius valley. This is a figure adapted from Fulton et al. 2017. As you can see from the LHS 3844b radius, it falls sort of right here in this peak of the terrestrial planet side of the valley. If you are familiar with other terrestrial exoplanet systems, I've actually made a 2-scale model. All of these planets orbit very similar sized stars, and this is their relative orbits. So you can see that LHS 3844 is just really, really tight in there. Okay, so I'm going to first start out kind of focusing on the planet, LHS 3844b. And this is some work that I did at the end of my thesis and came out last year. So I'll just kind of like jump right to the punchline, which is the transmission spectrum. So transit depth is a function of wavelength. And these, the data points are these 1 sigma error bars. And each of these is made from taking the weighted average of 13 transit observations from Magellan LDSS-3C. And we needed that many because with such a short orbital period, that gives you a short transit duration. It's those in-transit photons where you're really building up your signal. And I'd very much like to thank everyone who was involved in helping get the service observer program working at the CfA, because I was not going to be able to execute this program in person. So thank you for that. So the kind of main conclusion that we can draw from this transmission spectrum is when we compare it to some models, which are sort of there in the red and blue in the background. So we looked at a sort of solar composition, so that's to say a hydrogen and helium dominated atmosphere, as well as some higher mean molecular weight, pure water steam atmospheres. And we can rule out with these data a clear low mean molecular weight atmosphere around this planet, down to 1 bars of surface pressure at 5.2 sigma. So higher surface pressures are ruled out to higher confidence. We also can kind of address a cloud layer, so we can rule out low altitude clouds, but once you put a cloud high enough to truncate your spectrum such that it looks more like a flat line, we're not really able to address those as expected. So to put this in context of what we already know about this planet, this figure over here on the right is adapted from Kreidberg et al. 2019. And so they observed 9 orbits of this planet as it orbited around the star. And from that, they were able to get a phase curve. And the reason why that's important is that if there was a high mean molecular weight atmosphere on this planet, you would be able to see it advecting energy from the day side to the night side, and that would show up in the phase curve. And that phase curve would be sensitive to high mean molecular weight atmospheres down to about 10 bars here. So you can kind of a little bit ignore the y-axis on this figure, but I just sort of want you to focus on this x-axis down here with the surface pressure. So those phase curves ruled out high mean molecular weight atmospheres down to 10 bars of surface pressure. And then the authors kind of made more theoretical arguments, very reasonable, with stellar wind stripping to rule out atmospheres at lower surface pressures. And where this Magellan data fits in is to kind of address this middle ground here, where we can actually now rule out atmospheres down to about 0.1 bars of surface pressure for the low mean molecular weight case. And that's actually also kind of important because this method of trying to see the energy advecting from the day side to the night side in the phase curve is less sensitive to low mean molecular weight atmospheres because those are less efficient at advecting that energy. So the kind of remaining parameter space for this planet is a very tenuous high mean molecular weight atmosphere. And by some various arguments, you can show that that's a pretty fine knob to tune if you want to really put an atmosphere on this planet. So I think the main conclusion we can come away from is this is a bare rock. This exoplanet has no atmosphere to speak of, really. But I wanted to sort of move beyond this and think about, well, if it had an atmosphere, or if it at one point had an atmosphere, what would then be the interplay of that atmosphere with the host star, this LHS 3844? So now we're going to kind of switch over to talk about the star over here. And to look at it, we got 10 orbits of HST time with the Cosmic Origins Spectrograph, or COS, which has access to the UV part of the stellar spectrum. And we're interested in that UV part because that is the area that really drives atmospheric photochemistry as well as hydrodynamic escape. So even though the bulk of the flux is, of course, in the sort of optical to infrared, that's not as interesting for what could go on with the photochemistry in a potential atmosphere. So we got this data, and the first thing we did was to sort of just plot it out as a time series. And what I'm showing in this figure is the very first orbit. And it turns out we actually caught a flare in the FUV. So if you're familiar with COS, this is the G130M grating. If you're not familiar, this is just an FUV part of the spectrum. We needed to use a few gratings to cover the whole UV. And so this is one of the FUV observations. I didn't do a flare search for this. I just plotted the data and saw there was a flare. It's pretty prominent here. So now that we saw this, we were able to do some, kind of analyzing of the properties of this flare and maybe even compare it to other M dwarfs that flare more frequently. So that's what we did. And of course, the main point of comparison is the muscles sample. So this is a large sample of stars in the UV by HST COS and also other instruments as well. And I've sort of provided a lot of the properties here, but if we just focus on the absolute energy and equivalent duration, these are ways you can kind of compare flares in a more apples to apples way, even though they might be on different stars with different surface temperatures, different properties, things like that. These are good comparisons. And the only piece we're missing is we don't really have a great estimate of the flare frequency, right? We observed one flare in some non-contiguous data where we weren't really looking for flares. So we put like a very, very rough upper limit on the flare frequency of 4.9 plus or minus 2.2 days. So that's a very loose upper limit. I'm so sorry, this should say upper limit, not lower limit. It could always flare less. But basically, if you compare this to the muscle sample, it actually lines up pretty nicely with what you would expect within the error bars for the absolute energy and equivalent duration for this FUV flare. So that was pretty cool to see. And the other thing we were able to do is actually go a little bit upstream in the COS pipeline and actually excise these orange flare points from the data. And so then what we could do is actually make a quiescent spectrum and a flare spectrum for this star. And just keep in mind that this is already pretty low signal to noise data. So the flare spectrum is like super low signal to noise. So it's a very rough estimate. So now kind of moving on to think about, this is a time series, but we actually are, more interested in the spectrum. So this is the quiescent spectrum of LHS 3844. And I've sort of highlighted some, if you zoom in here, it's pretty noisy, but if you zoom in, these are real known UV lines. We saw them. But notably, if you know your UV, you'll note that over here at about 12, 15 angstroms, we're missing the Lyman alpha. And that's not because LHS 3844 doesn't have Lyman alpha, it's because COS is not good at observing it. There's two problems with Lyman alpha. One is that the core of the line profile gets extincted by the interstellar medium on its way to us. But the real problem with COS is that it has a fairly large aperture. And so you actually get a ton of contamination from the Earth's atmosphere, from solar Lyman alpha or ions interacting with Earth's atmosphere. So that's a problem. So we've just sort of removed all that contaminating Lyman alpha. But then we want to have some estimate to put back in, because the reason why you've probably heard of Lyman alpha and maybe not some other UV lines is because it is the most prominent in the UV, and it really makes up most of the UV flux from a given star. So in order to do that, we actually go back to the mussels program that I mentioned earlier. And because they were observing earlier M's that were a little brighter, they were able to observe Lyman alpha with HST STIS, which is another instrument. And this instrument has a slit. So they can observe the Lyman alpha without the geocoronal emission. They still have the problem of the extinction of the core of the line, but because they were observing, sorry? Yes?
I think you're okay to continue, Hannah.
Okay, I'll keep going. Because the extinction from the interstellar medium is still a problem, what they would do is build up flux in the wings of the Lyman alpha profile and then reconstruct the Lyman alpha line from that. If we wanted to do that, we would need about 70 orbits with HST STIS, and I don't think we would have gotten that time. So instead, we actually took the mussels results, which I'm showing a piece of up here. This is from Youngblood et al. 2017. And they found that with their Lyman alpha, their reconstructed Lyman alpha, along with a bunch of other UV lines they actually measured, they found these very nice correlations between the Lyman alpha flux and the flux of, say, silicon-3. And this was actually true of all the UV-UV line pairings that they looked at. So we took these correlations and took the UV lines we did measure and backed out an estimate of this Lyman alpha flux. These values here are actually the log 10 surface flux, which takes into account the stellar distance and radius. So you're kind of correcting for those different parameters in these correlations. So we did this for silicon-3 as well as a bunch of other lines down here, helium-2, silicon-4, et cetera. The blue bars are from the quiescent spectrum, and then the sort of extension to the orange bars are the flare spectrum. Because we only saw the flare and the FUV, we don't have all of the same lines we do for the quiescent spectrum. And then I just took some averages over here at the end. So this kind of teal bar is our final estimate of the Lyman alpha flux for the quiescent LHS 3844 spectrum, and similarly for the flare spectrum in the red. So that was fun. So now we can actually take the HST cost data and go even farther. And we ended up doing was making a panchromatic spectrum for the star from 1 to 10 to the 5 angstroms. So the HST data that I just mentioned is here. I've highlighted the estimated Lyman alpha line over here. And then redward, we've just kind of added a Phoenix model. We've extended it a little farther with a black body. And then over blueward is where it gets even more interesting, and we can actually take some Swift XRT data. This is from Professor Leah Corrales over at University of Michigan and her postdoc George King. And they looked at LHS 3844 with Swift XRT and were not able to detect it. So this is an upper limit. We then use this technique called a differential emission measure function, which I'm not going to get into because it's a little complicated. If you want to ask me about it, you can, but I'm sort of running low on time. So what I'm going to say is that you can actually now use a piece of this panchromatic spectrum, for example, to estimate the mass loss rate that LHS 3844b would have if it had accreted 1% of its mass in hydrogen and helium, which is about the estimate it might have accreted early from the protoplanetary disk, according to a paper by James Owen. And if that were the case, this flux, this highly irradiated planet would have lost that atmosphere in a mere 40 million years. So again, there's a lot of caveats here. For instance, earlier in the planet's lifetime, the star would have likely had a heightened degree of UV flux. But this is just kind of giving you a ballpark estimate of what we can do with a spectrum like this. And then finally, I just want to leave you with an even more hypothetical case that I think is really fun. So I'm a little bit cheating with the legend because this isn't actually LHS 3844b. This is a hypothetical Earth-like planet in the habitable zone of this system. But Eliza Kempton and her grad student Teal at University of Maryland were able to run a photochemical model for this hypothetical planet when you take the quiescent spectrum of the star as an input and then the flaring spectrum as an input. And even though this is a very hypothetical case, you can see even already some pretty interesting photochemistry happening here. So these dashed lines are where the quiescent spectrum is the input. And compared to the flaring spectrum, you can already see you get a lot of dissociation of things like water and methane. And then as they were explaining to me, quite a bit of interesting photochemistry happens with nitrogen and nitrogen dioxide. And that's actually where you're getting this additional O3 from. And then you can feed this all in to get a model transmission spectrum, and not very surprisingly, these two are very similar. So I don't think we'll be looking for atmospheric responses from flares in transmission, but it kind of ties the loop back to where we started at the beginning. Okay, that's all I've got. I will stop there. Thank you guys so much.
Thanks very much, Hannah.
Yep.
Really good work. So if we have any questions for Hannah, please raise your hand in the participant window. And I'm going to go straight ahead and ask a question myself. So with the transmission spectroscopy, you've ruled out, and for Laura's phase curve analysis, you've ruled out essentially that this planet doesn't have an atmosphere. But I was wondering whether you've considered looking for something like, looking for narrow sodium that might be ablating from the planet's surface, kind of like Mercury, which has a sodium tail.
Oh, that's interesting. I have certainly not considered that before now. I would think that would have to be a pretty, even if that were the case, that's a very tenuous amount of material from Mercury, so we can see it from here. But I don't know the actual signal to noise on that, but I imagine that'd be pretty tough to do for an planet like this. But yeah, it's an interesting thought.
Do we have any questions? If not, I have another one as well. So this, the flares that you see and the flare frequency that you have derived, would you expect to see that leading to a change in the secondary eclipse depth if the flares are heating the planet's surface to different temperatures? Would that make a noticeable difference in the secondary eclipse depth?
Yeah, again, I don't have like a number on this, but I'm gonna guess not. And that's mostly because this flare is, I mean, it looks nice and pretty here, but this is actually a very, very tiny flare. It's very small and it's very short-lived. This is like an equivalent duration, which is kind of like, and it's like analogous to an equivalent width, but like the actual duration is even less. It's only, you know, like a couple minutes long. So I don't think that's actually enough to be significantly changing anything that's going on the planet on longer time scales. The planet's spending most of its state experiencing the quiescent LHS 3844. But if you think kind of back in time when the star would have been more active, then I would maybe even think about taking the like flare spectrum as being the quiescent state kind of, you know, back at some point back earlier in the system's history.
Yeah, that makes sense. Thanks.
Yeah.
Prajwal.
Hi, Hannah. Great talk. Sorry, I was wondering to ask you about the flare model for the transmission spectra. I was wondering, when you have flare, you might introduce some ionized element into the atmosphere. So would you expect that to change the transmission spectra by a lot?
So I think, yeah, I mean, this is the sort of transmission spectrum. I think most of the problem is that transmission in and of itself would have a hard time picking up those differences anyway. If you could get, you know, this is a very small planet around a relatively dim star. If you could get better emission spectra from it, and it had an atmosphere, that might start to be possible. But I think what we've sort of shown here is that the transmission spectrum is not being significantly affected. Certainly not something that I would, you know, like write a proposal to look for. Yeah.
Thank you.
Yeah, thank you.
Do we have any more questions for Hannah? Prajwal, do you have another question, or is your hand just still raised? Nope. Okay. Well, in which case, thanks again, Hannah.
Thank you.
And we can move on to our second speaker. And Sam is going to introduce our second speaker today. So go ahead, Sam.
Okay. Yeah. So our second speaker today is Spencer Hurt. Spencer is started as an undergraduate at Harvard and transferred to University of Colorado Boulder. His research focuses on detection, characterization, and formation of exoplanet systems. And today he's going to tell us about a decade of radial velocity monitoring of Vega and new limits on the presence of planets. So Spencer, I'll let you take it away.
Thank you so much. As was just said, my name is Spencer, and today I'm going to be talking about some work I've done on the Vega system. But before I begin, I'd just like to give a big thank you to everyone who's worked with me on this project, especially Sam Quinn and David Latham. Vega is an incredibly bright and well-studied A-type star that we view approximately pole on from Earth. And it also happens to be one of the very first systems that we detected circumstellar debris in. For example, here we have an ALMA image of the outer debris belt, which has consistently been used to suggest the presence of planets somewhere around 60 AU or other large orbital radii. However, there are other supposed structures in the system that have pointed towards the presence of other potential planets at a wider variety of orbital locations. For example, infrared excess suggests that there's a lot of hot dust close in to the star. And for us to replenish this region of hot dust, we would need something like a chain of planets to scatter comets inwards. Because this system has consistently pointed towards the presence of planets, a lot of people have taken an interest in Vega, particularly direct imagers, because Vega is a prime target for direct imaging. After all, it's bright and would be able to illuminate a lot of faint targets. We view the disk approximately face on and the star approximately pole on, meaning any planets well aligned with the system would be visible pretty much throughout their entire orbit. And it's also just a large system, meaning there is a good chance that there are planets far away from the star where you would have enough contrast from that starlight. And so these direct imaging surveys haven't really been successful in finding any actual orbital companions. Instead, they've only been able to place detection limits like the ones that we see in this figure here. And while they do have pretty good sensitivity at pretty far orbital radii, for example, at the very edge of the system, they have sensitivity down to Jupiter masses, we see that in the inner 15 AU, it's just simply too bright for them to rule out anything smaller than a brown dwarf or even larger companions. And as a consequence, we need to look towards some other method to really explore this inner region like radial velocities. While the star's pole-on status does pose some challenges for an RV search, we know that a lot of planets, in particular hot Jupiters, could appear on misaligned orbits around stars above the craft break, which would be ideal for us observing a pole-on star here from Earth. Additionally, this means that the projected rotational velocity is quite low, and we are able to avoid a lot of problems like rotational broadening that are quite common to a lot of A-type stars. It just so happens that David Latham's research group has been gathering radial velocities of Vega for over a decade. As Dr. Latham likes to say, these observations are essentially free because we're able to observe Vega during twilight, meaning we aren't really eating into observing time that we can allocate towards other targets. And in total, we have about 1,500 spectra. Now, our derived RVs are a little noisy. They have a scatter around 20 to 30 meters per second. However, we find that we have enough data spanning long enough of a time to really build up sensitivity to a lot of short period signals. When beginning analysis of this data, we immediately see that's dominated by a signal at 2/3 of a day, which is shown here with red in our periodogram, along with a lot of other peaks that actually correspond to the harmonics and aliases of this signal. And the signal happens to be synced with the star's rotation period, which isn't necessarily surprising because previous spectroscopic studies have detected Vega's rotational modulation. Now, the signal, of course, is really frustrating in the context of searching for planets because it's strong and it obscures a lot of other weaker signals. However, it's also really interesting on its own because Vega's, once again, an A-type star and shouldn't have a magnetic field or surface features to begin with. Our data set spans long enough of a time that we have a unique opportunity to investigate how these active regions and surface features evolve over time, which in turn can actually end up pointing towards the origin of Vega's magnetism. We end up actually modeling our data using a quasi-periodic Gaussian process. And throughout with this model, we find an exponential decay time scale of about half a year, which would commonly be interpreted as the lifetime of these active regions. But we can also explore how this signal evolves over time more qualitatively by looking at a stacked periodogram. Here we see that the signal cycles in strength over a period of several hundred observations, or in other words, several years. And towards the end, we actually see that the location of the tallest peak in this region actually shifts. Combining these two different results, we actually believe that these active regions have lifetimes that are much more long-lived than the star's rotation period, which would point towards some mechanism like a failed fossil field as driving Vega's magnetism. Specifically, a failed fossil field would likely appear during the early stages of the star's formation. Now, we also wanted to explore this activity signal at a higher cadence. And because test pixels overflow instead of oversaturate, it offers a prime opportunity to do really precise photometry of stars as bright as Vega. And tests observed Vega during sectors 14 and 26, with the light spilling over into about 4,000 pixels, just to emphasize how bright the star really is. And here we have data processed for us by Andrew Vanderberg. And while the light curve does look relatively flat, if we feed it into a periodogram, we immediately see a peak emerge at 2/3 of a day, making this the very first photometric detection of Vega's rotational modulation. Now, there are a couple of really interesting things to note about this signal. First off, there appear to be a lot of outliers within our data set, particularly sector 14. And if we clip these outliers before running our periodogram, we actually see the strength of our signal decrease, suggesting that these outliers aren't instrumental, but instead that they point towards something like rapid evolution amongst the star's surface features. This would actually point towards an additional mechanism for Vega's magnetism, such as dynamo action in a very thin convective layer. While the different competing sources for Vega's magnetism aren't necessarily mutually exclusive, we really should look towards additional observations such as long-term high cadence spectropolarimetric observing to really constrain how these active regions evolve over time and where Vega's magnetism could be coming from. The second really interesting thing to draw from this light curve is just how shallow our signal is. It only has amplitude of about 5 to 10 parts per million. If we take a quick look back at our radial velocities, we had an amplitude of about 10 to 15 meters per second. And if we examine the relationship between V sin I, RV amplitude, and photometric amplitude for a dark spot, we actually anticipate a photometric variation more on the order of 200 parts per million. It's pretty clear that the signal that we're seeing can't be caused by something like a dark spot, and instead we believe the stellar surface is dominated by bright plages, which are characterized by relatively low flux variation, but much larger spectroscopic signals. So now that we've looked at this activity signal in depth, we can really begin to search for planets, which I know is the reason why we're all here. We need to begin by first accounting for this activity signal because it is extremely dominant and it makes it difficult to discern what signals might be noise and what else isn't. And so while I previously mentioned using a Gaussian process to model our rotational modulation, we find that we really don't have high enough of a cadence to constrain the high frequency hyperparameters. And as a consequence, our model ends up overfitting and our residuals really aren't all that useful. Instead, we use successive Keplerians to account for this signal. And we illustrate the fitting process in this figure here, where each periodic corresponds to the data after removing a Keplerian signal corresponding to either the rotation period or one of its aliases. And we see that it does remove this rotation period along with its peaks corresponding to its aliases quite well. And throughout this process, there's really only one peak that goes unchanged, located here at 2.43 days. If we facefold and bend our data to this periodicity, we see that it does correspond pretty well to a Keplerian orbit, but it's not really significant on its own. So we don't consider this to be an actual planet, but instead a planetary candidate with a minimum mass of about 20 Earth masses. Of course, if it were misaligned with our line of sight and even well aligned with the star's spin axis, it very easily could be a Jovian companion. One really interesting thing to note is that if this were an actual planet, it would make Vega one of the hottest stars to have a known planet surrounding it. And because it's on such a close-in orbit, it would have an equilibrium temperature of just over 3000 Kelvin, which would point towards, which would actually put it in line to be the second hottest planet ever detected, just after Kilt 9b. One really interesting implication of this is that if the planet isn't stripped of its atmosphere, it very easily could have atmospheric emission lines, which also offers an opportunity to verify its existence by searching for atmospheric emission lines within spectra of Vega. This is especially interesting when considering the fact that radial velocities are a time-consuming process when trying to even make a marginal detection of this signal, particularly because our data is dominated by that rotation period. From there, we're able to go on to place new detection limits for planets in this inner system using radial velocity injection recovery tests. And we really consider two different regimes here. First off, we look at the case where planets are isotropically distributed around the star, which is particularly relevant for companions such as hot Jupiters. But we also consider the case where planets are well aligned with the star's spin axis, which is probably more relevant for smaller planets or maybe planets at further orbital distances. Of course, in the second regime, our sensitivity is a lot worse because we view Vega pole-on. And so we actually combine our data with direct imaging results to account for this dense blue region in the corner and provide a more comprehensive limit for planets in the entire system. Combining these two different results, we're really able to provide a tight limit on a lot of massive companions such as brown dwarfs or larger objects, regardless of their orbital geometry or orbital inclination relative to the star. Additionally, we do have sensitivity to a lot of massive planets, really regardless of their orientation relative to the star. we're able to rule out most things larger than 8 or 9 Jupiter masses if they're close into the star. And in the isotropically distributed case, we have sensitivity to sub-Saturn masses, which would indicate that if there is a hot Jupiter around Vega, in most cases, we would be able to detect it. From here, we're also able to go on to use our test light curve to place detection limits on transient planets, which again is also most relevant for hot Jupiters, given those are the most likely to be on an edge-on orbit around a star that we view a pole on here from Earth. And using transit injection recovery tests, we have formal sensitivity limits that are able to rule out really anything larger than a Neptune, as long as it is on an orbital period less than 15 days. At larger periods, our sensitivity begins to fall off because we get gaps in our data, or maybe a transit only appears once in the entire test light curve, meaning we can't really constrain its period, and therefore we don't count it as a detection. But we know that any planet larger than 2 Earth radii would have a transit depth of about 50 parts per million or greater. And if we take a quick look back at our light curve, it's pretty clear that we probably would be able to see a transit depth of 50 parts per million simply because it's so quiet. So realistically, this limit or these limits are more conservative. I think one really interesting thing to look at is how these limits will hold up in the future, especially as we consider direct imaging missions that are coming up, such as JWST or the Roman telescope. And previous work has actually looked at what JWST's detection limits will be for Vega. And we see that they don't really cover the same region that we're looking in. The instrument's inner working angle obscures the inner 15 AU, although they will be able to provide much tighter constraints on planets in the outer system, which definitely provides more insight still towards whether or not there could be a chain of planets around Vega, which would also still be interesting in the case of the inner system. When it comes to the Roman telescope, the CGI does have a lot smaller of an inner working angle, and so we'd be able to explore a region or a portion of this inner region, really into about 6 AU, which would complement our results quite well, given that's where our sensitivity begins to fall off rapidly. That's specifically because 6 AU is about where our decade of data stops covering a full orbit. So mostly in summary, by combining our radial velocities with test photometry, we're able to investigate Vega's activity signal and try to constrain the origins of its magnetism, while also characterizing the types of active regions that dominate the surface. Along with that, we identify a short period planetary candidate that could potentially be verified using high resolution spectroscopy. And then we also place new detection limits for planets in the inner system. With that, I'd be happy to take any questions.
Thank you, Spencer. Do we have any questions? I'll ask one. What are the prospects for adding limits from astrometry in the future?
Yeah. So we actually kind of looked at this in our paper. It's hard because with an instrument like Gaia, when you encounter bright stars, astrometry becomes a lot harder. Simply because there aren't like there aren't like the pipelines to process a lot of that data, or they need different observing modes. And so it's not really clear whether or not we could achieve higher precision with an instrument like Gaia, but it doesn't seem very promising.
So I realized I can't raise my hand because I'm also a host, so I'll call on myself. Yeah, I was curious if I don't remember what the resolution of trace is.
I think it's around 44,000 per element.
Okay. So if you had, I mean, that's pretty high resolution and you could, maybe get higher at some point. Would you be able to actually detect, the planet's atmosphere and therefore the planet that way?
Yeah, so that's actually something that Sam Quinn has been looking into. One thing is, I can't remember the exact numbers because he's definitely the one that's been looking into this more than me, but I think the lines, the way that they would shift, if you're looking at the cross correlation, is only like 1 pixel in trace. So it definitely would be a very difficult detection to make. and probably would be easier to do with something like a more high resolution instrument. There are other data sets for Vega that just really the thing that distinguishes them from ours is the time span. But there have been previous studies with like SOFI that will have basically continuous data for 5 days that could potentially be better suited for something like this. But
Cool, thank you.
Spencer,
Thanks.
could you comment on the future plans for observing Vega with trays?
yeah, that's probably something that you'll have to talk to Dr. about. But from what I understand, because they are free observations, I mean, they aren't really interfering with our other targets of interest, and because there is a potential planetary candidate, something that's worth continuing observations of.
Are there any further questions? Oh. Dave, can you repeat? That was kind of quiet. Okay.
Are you talking to me?
Did you have a question, Dave? I missed.
No, I'm just stating that we will keep observing Vega for free in twilight. For another 10 years? I don't know.
Does observing in twilight have any like lasting biases on your data?
Well, by twilight, I mean before you can do 10th magnitude stars, and Vega's 10 magnitude brighter. So even if there's a little bit of scattered sunlight, it doesn't matter. It's really tiny.
All right, if there's no further questions, let's thank both our speakers again. And